Welcome to our Signal Media Executive Interview Series. I'm Kimberly Underwood, Director of Digital News Media at AFCEA International Signal Magazine. Welcome to our latest episode, which is sponsored by Mercury Systems. Today, we're going to be delving into radio frequency, or RF, technology advancements that are offering solutions outside of traditional receivers and transmitters. For RF communication, virtually all electronic defense systems require signal processing. And the first requirement of any of these systems is usually to convert the signals from analog and to digital to enable processing. And then often that is converted back to analog after processing. In recent years, interest has grown in signals higher in the RF spectrum, and this has certainly created challenges for data conversion as well as the processing engines that are needed. One advancement has been the area of so-called direct RF data converters. And with me today is Bob Sgandurra from Mercury Systems, who will walk us through all of this. I also wanted to direct you to a white paper from the company that you should check out called The Need for Direct RF in an Evolving Defense Environment. A little background on Bob. He is the Director of Product Management in the Mixed Signal Division at Mercury Systems. Before working in the defense industry, he spent 7 years in the medical electronics field, where he designed products and managed product teams around ultrasound imaging. Bob joined Pentech, which is now part of Mercury, in 1994, working as an application engineer and system integrator, where he concentrated his efforts on solving the real-time technical requirements of customers. In 1997, he took on the responsibility of product manager at Mercury Systems, and he's taken off since then. He holds a Bachelor of Science degree from the New York Institute of Technology. Bob, hello, and thanks so much for sitting down with me today.
Thanks, Kimberly. Thanks for having me.
Bob, can you walk us through what is direct RF and what are the main advantages? Thanks.
Sure. As you kind of mentioned in the intro, most electronic defense systems need to digitally process analog signals. And it doesn't really matter whether it's signal intelligence or electronic intelligence or radar or electronic countermeasures, you still need to digitize that analog signal. So up until about 10 or 12 years ago, we were seeing data converters with maximum sample rates in the hundreds of megasamples per second range. So if you need to digitize a signal that's much higher in frequency, say 12 gigahertz, the first thing you need to do is send it through an analog tuner stage that can contain things like a local oscillator and mixer and other analog filters. And it takes that frequency, let's say at 12 gigahertz, and it translates it down to an IF or an intermediate frequency that can be digitized by the analog to digital converter. And that's pretty standard. That's been done for many, many years. But what's happened in the past decade or so is the data converter manufacturers are making A to Ds and D to As that are sampling at much higher sample rates. So now you can see more of the RF spectrum directly by the A to D. You don't need to have that analog translation stage. And, you can question, like, what's direct RF? If you asked me that 7 or 8 years ago, I'd say direct RF is us sampling at 4 or 5 gigahertz. Today, we're sampling at, 10 times that. So direct RF really is a function of what technology exists and also what kind of application requirements, you're trying to service.
Right, sure. And can you talk about some of those technological advancements that have enabled direct RF to be a solution?
Sure. What you're seeing is advantages like swap, size, weight, and power. That's something that direct RF brings to the table. By eliminating the analog transition stage or the translation stage, you're eliminating those components, and that can help in size, weight, and power. If you think about an application like a phased array antenna, an AESA, where you can have 100 or even 1,000 antenna elements, every one of them is a channel that requires data conversion. So if you can have a savings in power and cost on a per channel basis, if you times that by 1,000 channels, you can see the swap savings pretty quickly. Another advantage is the higher sample rates give you a much wider bandwidth to sample simultaneously. So if you have an application, for instance, that has signals that are transient, maybe your signals are popping up and they're disappearing, or they're frequency hopping, you need to see all that and maybe, acquire those signals. So in a traditional analog tuner, usually you have a small bandwidth that you scan across the wider spectrum. And if a signal is occurring outside your tuning range, you're going to miss it. But with direct RF, you can stare at a much wider swath of the spectrum. You can detect those signals. You can use additional direct RF channels with digital down converters to zoom in and start tuning on those signals. And then you can also maintain that wide stare, so you won't lose track of other signals appearing and disappearing. On the transmit side, you have the same functionality. You can take the signal you want and output it anywhere within that range. And you can also use multiple channels to do very precise beamforming. By eliminating the analog components in that translation stage, you're taking components out that could potentially drift in frequency or in phase over time and temperature. So you can create a much more precise synchronization scheme, and that's critical for precise beamforming. And also, you're eliminating components that might, age over time and need to be replaced. So you're also lowering maintenance costs.
Right. Those sound like some really great advancement areas, especially in, near peer environments
Mhm.
that, our military will be facing. And then can you talk about kind of, at the beginning you spoke about obviously in RF processing, signals intelligence, radar, countermeasures, but what applications can benefit from direct RF? Is it still kind of these areas? And can you give some examples? Thanks.
Sure, it certainly is. You can see advantages in, again, the high channel count systems, right? There's a swap savings. What you're seeing is a trend more and more towards applications where you want to put the data conversion and the data processing right behind the antenna. So if you're minimizing that circuitry by taking out that analog transition or that translation stage, you're creating a smaller digitizer. Now you can put many channels of digitization, right behind the antenna array. Um, One of the other things that you see is also manufacturers like Xilinx and AMD. They're putting those data converters right inside the FPGA or right inside the same package. Altera's doing it, Intel's doing it. Well, actually, Altera is Intel, Xilinx, AMD. And that intimate connection between the A to D, the data converter, and the FPGA fabric gives you a very low latency path. Having the direct RF converter, let's say, in a package and having the FPGA in a separate package, that serial interface to connect, adds latency. So for applications like electronic countermeasures, DERFMs, having that low latency path where you can receive, you can process, and you can retransmit in a very small time window is really critical. Direct RF, brings that advantage that I don't think you can really do that without an integrated solution.
Right, sure. And the FPGA you were talking about it, that's field programmable gate array.
Right.
So I guess you're seeing kind of manufacturers responding to this new solution area. Um, are there any disadvantages though of using direct RF technology, or any challenges still, or drawbacks?
Yeah, I mean, you can see some in general when you're moving up in sample rate, you're also moving down in bit resolution. So that equates to lower dynamic range. So a 12-bit or a 10-bit data converter is probably fine for a lot of applications, even in countermeasures. But if you're looking at an application like maybe SIGINT, where you have a very small signal, a very low power signal that you're interested in sitting right next to a very high power signal, you might still need that dynamic range. So in that case, you might want to use an analog tuner. You might want to take that RF signal, translate it down to something that, let's say, a 250 megahertz sampling A to D at 16 bits can sample, and that'll give you that much wider dynamic range to see that signal. And then, that's an example where you might not want to go direct RF.
Got it, sure. And then can you kind of talk about the landscape of direct RF? What does that look like these days,
Sure.
especially in the last couple of years? Who are the players and who are the vendors, converter and processing vendors that you're seeing?
So the players you expect to see, the manufacturers, are the ones that we've always seen: Texas Instruments, Analog Devices. Texas Instruments has their AFE family of products that are transceivers, direct RF transceivers. Uh, Analog Devices introduced, I guess it was mid last year, their Apollo family of MXFE parts, which are very interesting. Their A to D is running at 20 gigasamples per second, and D to A is running at 28 gigasamples per second. A relatively new player is Jariat Technologies. They have a 64 gigasample per second A to D and D to A at 10 bits. And that, as you'd expect, has gotten a lot of interest. And these are all data converter components, again, using a separate FPGA. But, starting in 2017, when Xilinx introduced the RF SoC, or the RF system on chip, that really kind of changed the landscape. What happened was that it started bringing FPGA manufacturers into the direct RF solutions. And when they introduced RF SoC, what they did is they took their UltraScale Plus fabric, put eight 4 gigasample per second A to Ds and eight 6.4 gigasample per second D to As right on the same die. And that was really revolutionary. We saw that used in a lot of different applications, even ones that weren't direct RF or what you'd consider an RF application, because it was really a diverse, very flexible chip. You could use it in a lot of different ways. They increased that performance a few years later, getting up to 5 gigasample per second A to Ds and almost 10 gigasample D to As, all running at 14-bit. And then, of course, Intel, wasn't going to stay in the background. So they introduced a 64 gigasample per second A to D, D to A, originally on their Stratix 10 part. And now in the last year or so, they've introduced it in their Agile X fabric.
Yeah, those are great advancements. How about, are you seeing anything kind of on the government or military side where they're funding programs to advance direct RF technology?
Yeah, you definitely are. There's multiple programs out there. I mean, the CHIPS Act is definitely putting money into direct RF. Another one that's kind of interesting is the STAMP project. And STAMP is funded by DoD. And the purpose of STAMP is to take technology, either conceptual or chip level technology, and allow that technology to be absorbed by products that vendors like Mercury could make, which are board level solutions. So STAMP helps fund that development. So you can take this technology and get it into the DIB and widely distribute it for different applications. So that's actually a really interesting program.
Right, sure. And then what does the direct RF roadmap look like? What should we expect in the next couple of years?
Sure. Like I said, today we have data converters that are running at 64 gigasample per second A to Ds, D to As at 10-bit. And that's still within a range that gives you the resolution you need for a lot of these applications. I certainly expect to see, higher converter rates in the next few years, maybe 100 or even 120 gigasamples per second, let's say in the next 4 or 5 years. And then again, the problem with that is with these higher sample rates, you have so much data to deal with. So advancements in FPGAs are also, or processing is also really part of this roadmap. Today, you see, again, chips that have built-in functionality like digital down conversion, up conversion, beamforming, and that helps you offload some of that processing to a part of the processor that's really dedicated and does that task very well, and it frees up a lot of the FPGA fabric. I think you're going to continue to see that, but you're also going to continue to see maybe specialized processing. Mercury and Intel are using chiplet technology to build these multi-chip packages. And what that allows you to do is the chiplets are specialized dies that'll do conversion, or they'll do processing, or they'll do memory. And by combining those into a single package, you're seeing more efficient processing of these higher and higher bandwidths. Also, the FPGAs themselves are moving up in their gigabit serial interfaces. So the newest FPGAs you can put protocols in there to run 100 gigabit Ethernet or 200 gigabit Ethernet right on the chip. And in applications where maybe you want to sample the data and then maybe send it to a second processor for additional sampling, or maybe store it, on a data recorder, you need those really fast pipes to get the data in and out. I think some of the peripheral technology, like even the thermal management, is going to be critical, because even though you're taking the overall power of a system and you're reducing it by eliminating, let's say, some of the analog components, or you're combining different components in there in a single package, so you don't have the interface circuitry that takes up power, you're lowering the overall power, but you're also putting a lot of technology in a very small package, right? You're putting A to Ds, D to As, converters. So thermal management for those parts, because they do get relatively hot, is critical. So I think we're starting to see, and we're going to see more efficient thermal materials, more directional materials to move data off chip and through heat sinks. Technologies like air flow through, liquid cooling, which exists today, I think we're going to continue to see advancements in those. all to enable, what is basically this direct RF marketplace.
Right, sure. And for that kind of specialized processing, in these chiplets, what do you hope to see? Where do you think that's going to take capabilities, I guess, for the military?
Yeah, I think again, you're going to see in general, data acquisition is going to need to go faster. In terms of actual processing, beamforming, whether it's radar or it's communications, is a big part of it. So having more efficient beamforming in there in these chiplets, we didn't really talk about it, but secure processing is very, very important in many of these apps. And part of those dies can be part of supporting a secure processing environment. So, I mean, the beauty of having a chiplet type solution is that, you can introduce functionality in a chiplet. And I mean, it's not a trivial thing to make a system, a system and package, but at the same time, you can mix and match those functionalities easier than creating an entire new die with all that functionality.
Right, sure. Sounds fascinating. Those are all my questions. Anything else you wanted to highlight or paint a picture for the future?
Yeah, no, I mean, it's really interesting technology that we've seen advance over the past 10 or 12 years. And, the FPGA manufacturers getting in the mix and combining all those technologies enable applications that you just couldn't do. We're going to continue to see that. And they're going to see things that we haven't even thought about yet in the next couple of years, I'm sure, that are going to start, integrating these solutions even better. So,
Right, sure. Well, thanks so much, Bob. And for our audience, check out that white paper from Mercury Systems. Then it's called The Need for Direct RF in an Evolving Defense Environment. Also, take a look at their website. There's more information about their capabilities there. It's mrcy.com. And anything else, Bob?
no, just thank you for the time today.
Yeah, thank you so much. We really appreciate your expertise. Thank you.